Hi, Year 10. This week we are going to go through our next topic in Core Technical Principles. That is a systems approach to design. So this is where we look at a little bit of electronics and how different systems work in response to changes in the environment. So can you turn to this page in your booklet and write down the learning objective, which is I will learn how we use a systems approach when designing. Fantastic. So, what is a systems diagram? To put it briefly, it's a diagram that breaks down an operation into its three main parts: input, process, and output. When we say an operation, generally speaking, it's talking about an electronic device or an electrical system where it has an input which sends a signal to a component that processes that input and sends a different signal to an output device to do a specific function. So let's write down what an input, what a process, and what an output is. So an input device takes a signal from the physical or real world and turns it into an electronic signal that a process device can understand and act upon. What that means is that the physical or real world input could be someone pressing their finger against a light switch. It could be the sunlight getting brighter in the day. It could be the pressure of a weight on a pressure pad. It could be the temperature increasing or decreasing. So it's a signal in the real world, something in the real world that changes. The input device will take that and create an electronic signal which is sent to a process device. So when the process device gets that signal from the input device, it acts on it by changing it in some way. So it will take that input signal and change it to a different outgoing signal, which is then sent to the output device. So process devices take the signal from the input stage of a system and acts on it by changing it in some way. For example, counting the number of times something happens. And then finally, the output stage is where we have an output device that takes the signal from the process device of a system and turns it back into a physical or real world signal, such as light or sound. So this whole process starts as something happens in the real world environment. So say, for example, the temperature increases by 3 degrees. The input device will recognize that change, that signal in the real world, and create an electronic signal that is sent to a process device. That signal tells the process device, oh no, we're 3 degrees hotter now, and that might then send a signal to an output device, which might be an air conditioning unit, and the air conditioning unit might turn on, therefore pumping cooler air into the room. So systems diagrams are breaking down an electronic device into input, process, and output devices, and they all have different uses. So for example, turning on a light switch, that is the physical movement of you pressing your finger against that switch is the input, the signal from the real world. The input device will send a reaction signal to the process device, which is let's turn this light on or let's turn this device on. Let's send electrical current to it. And then that goes to the output device where it creates a real world signal. In this example, the light will turn on and the real world signal is producing light. So that is the basic breakdown of what a systems diagram is. Later on in this video, we are going to look into what the different types of devices are and how they work and where they can be used. So for that to happen, we need to turn to the next page in our booklet and write down the learning objective, which is I will learn how different input devices are used in circuits. When I say circuits, I mean electronic circuits in electrical goods. Write the learning objective down now. Fantastic. So we have got 3 different types of input devices here. These ones are all sensors. So an input device is an electrical and mechanical sensors and switches that use signals from the environment and convert them into signals to be passed to processing devices. So we're going to look at sensors to begin with. Light-dependent resistors, thermistors, and pressure sensors, these are all sensors. They are used to detect changes in light, temperature, and pressure. So the first one, an LDR, is a light-dependent resistor. What it is a component whose electrical resistance changes with light levels. This is used as an input device in light sensing circuits. So we need to be writing down this information in our tables. We've got our revision material as we go through this video. So what that statement means is that when it is really light outside, for example, the LDR will absorb that light and then change its resistance to accommodate that. So it will increase the amount of electrical resistance of the device, which means that it will not allow as much electrical current to flow through the circuit. So much so to the level where a light bulb might not turn on. But when it gets dark, the amount of electrical resistance that the LDR provides reduces, so it gradually lets more and more electrical current flowing through it until it gets to the stage where it's dark enough that it will just let all the electrical current through, therefore turning the lamp on, the bulb on, or the light on. So the uses for these are street lamps, night lights, mobile phones. So in our mobiles, you know, when you walk into a dark room and suddenly your phone brightens up, or you walk outside and your phone dims, your phone has a very, very tiny light-dependent resistor in it, which is picking up on those light levels and changes the brightness of your screen so that it's more comfortable for your eyes. Okay, our second one is a thermistor. So clues in the name: thermo. So it's all about temperature. So this is a component whose electrical resistance changes with temperature. This is used as a device in temperature sensing circuits. So very similar to the LDR, but with temperature. So as the temperature increases, the resistance might increase, and it will stop or harshly reduce the amount of electric current flowing through the circuit, therefore turning the output device off. But when it gets cold, there's less resistance, so the electrical current can go all the way around the circuit, meaning that the output device will be able to turn on and produce heat. So for example, toasters, fridges and freezers, hair dryers, coffee makers, they all have thermistors in them. Good example are toasters. So if you put your toaster onto setting, I don't know, setting number 5, that will then mean that when the temperature hits a certain point, a certain temperature, the thermistor's increased resistance will cut off the electric supply and then turn the toaster off, meaning you've got the perfectly toasted piece of bread or bagel or crumpet, whatever takes your fancy. But it's also used in safety functions in hair dryers and like heating products, because it will, if a device gets up to a certain temperature and above a certain temperature, the thermistor will cut off the electrical supply going around the circuit, therefore turning the device off, the hairdryer off, and reducing the risk of injury to a human using that. Okay, our final type of sensor input device are pressure sensors. These produce a signal that varies depending on the amount of pressure placed on them. So similar to a light-dependent resistor and a thermistor, but the amount of resistance or the signal that it sends to the process device is dependent on how much pressure is placed onto the sensor. And the main use for these are in security systems. So pressure pads in the floor, so when you lock up a building, if someone manages to break in but walks across the floor, the pressure sensors will pick up on that and the alarm will go off. So I'm going to pause here and make sure that you've to allow you to write down all of these notes, and then we'll move on. Fantastic. Our next type of input device are switches, and switches allow current to flow through them when contacts inside are joined together. So switches make or break an electrical circuit. They either break it apart, so there's a gap in the circuitry, so the contacts are not touching, meaning that electrical current cannot flow through the circuit, therefore turning the device off, or it makes the circuit. So it will make the circuit whole, so there's no gaps, allowing electrical current to flow through it. We are going to look at three different types: rocket switches, push to make, and push to break. Rocket switches are your simple on-off switch, like a light, like an electrical switch on plug sockets. These are used for light switches and plugs. The next two are slightly different. So the push to make only allows current to flow through it when pressed, therefore making the circuit. So you have to apply pressure down on this push to make switch to keep a device on. As soon as you release pressure from it, it will break the circuit. So you're pushing to make the circuit work. You're pushing to allow electric current to go through. And these are used for Xbox controller buttons, or basically any remote or anything with a push action button. So for example, when you're on the Xbox or PS5 playing whatever, Call of Duty, pressing the X to jump or shoot or fire, that is a push to make. As soon as you press it, it allows a small burst of electrical current to flow through the circuit, therefore telling your device, your games console, that you want your character to jump, and that happens super quick. Our last type is push to break. So it's basically just the same as the push to make, just in the opposite way. So when you push down on a push to break switch, it stops the flow of current, therefore turning the product off, breaking the electrical circuit. These are also used in controllers and remotes, anything with a push action button, your keys on a keyboard, your on off button on your phone. So pause here, make sure you've got all of the notes down in your book, and then we're going to move forward. Fantastic. So fine, then we've got process devices. This section will be quite quick because we've only got one type that we're going to look at. So pause the video here and write down the learning objective, which is I will learn how microcontrollers are used as process devices in circuits. Fantastic. So what are microcontrollers? They are basically a small computer with a single integrated circuit. So they're similar to a microchip. They are the brains of a system's approach to design. It's the brains of a electronic product, an electronic system. It takes the signals from the input device, the switch, the thermistor, the LDR, whatever it may be, and it converts it into a very specific outgoing signal that will tell the output device what to do, whether to turn a light on, whether to turn the heating on, whether to turn the heating off. So the advantages of these is that the size of the circuit can be greatly reduced because these are now super small. They're tiny little things, and they have allowed electronic devices to be greatly reduced in size, such as like flat screen TVs or PC computers. They used to have these huge backs to them because they had so much hardware, but now you can have really slimlined computers because of these microcontrollers. They can be reprogrammed many times, so they don't just do one thing. You can reprogram them to do different functions. And finally, they have pins for connecting several input and output devices. So a microcontroller does not only do just one input and one output. It doesn't just process one, it can process multiple systems. So you can have one microcontroller in an electronic device controlling all of your different functions. So an Xbox controller would have one or two microcontrollers that handle every single one of the functions within that device. The disadvantages, however, they are much more expensive than traditional circuits, but I would say the benefits greatly outweigh the extra cost of that. The reprogramming software and hardware required is very expensive as well. And it's also very difficult to use because you need to understand the coding and the language the system needs to be able to do specific things. So lots of different microcontrollers have different coding languages, and you have to kind of know all of them to be able to efficiently reprogram different types of microcontrollers. So pause the video here, get all that down, and then we will move on. Okay guys, last part. So output devices. Turn to this page in your booklet, write down the learning objective, and then we will crack on. So the learning objective is, I will learn how microcontrollers are used as process devices in circuits. Fantastic. So we have got four we're going to look at. So we have got bulbs, LEDs, buzzers, and speakers. You've probably heard of all of these before. These are all devices that are able to take a signal from a microcontroller, the processing device, and convert that into a real world signal. So the first two produce light in response to signals from a process device, and the other two, buzzers, speakers, produce sound. One quite a simple sound, and the last one more complex because of the electrical audio signals that pass through them. So the first one is a bulb. This is a light output. So when current flows through the filament, it heats up and light is produced. This is an old school filament bulb. Make sure we're adding our notes in our booklet. The second one, LED, light emitting diodes. They are also a light output, and they also light up when current flows through them. When I say current, I mean electrical current. Okay, and then the last two, these are our sound output devices. So a buzzer, when current flows through a buzzer, it produces a buzzing sound. They are used in products such as doorbells, alarms, alarm clocks, anything that has like a buzzer, a fire alarm. So doorbells and any type of alarm, basically. So when electrical current passes through it, it creates that buzzing sound. And then finally, your speakers, they are also a sound output device, and they produce sound using electromagnetism. So they actually with the aid of a microcontroller, the process device, it is able to convert electrical audio signals into sound waves that we can hear. So that is how we listen to the radio, podcasts, any music, anything is through electromagnetism. Pause here and get all of those notes down, and then we will wrap up. Awesome, guys. That is the end of this week's video lesson. If you've got any blanks in your booklet over the last 3 pages, please make sure you rewind in the video so that you've got all of the notes in your booklet. Thank you for watching, and I will see you in class. Goodbye.